Okay, thank you. And first of all, I would like to briefly remind you what we call orbital binary. Orbital binary is a visual binary with known orbital elements and, as a rule, with known distance. In my talk, I will describe goals of our work. Then I will speak about compilation of a list of orbits. Then I will give some ideas about construction of refined list of pairs, and I will display you resulting parameter distributions. Our goals are to construct a largest list of orbital binaries containing orbital elements, magnitudes, spectral types of components, distances, and indication on spectroscopic and eclipsing nature of systems. Then we would like to estimate dynamical masses of orbital binaries. We also can estimate photometric and spectral masses. I will later remind you what is this. And we intend to make some preliminary conclusions on distribution of systems along principal orbital parameters like period, semi-major axis, eccentricity, and masses of the components. Of course, as a base of our study, we used two well-known and widely used catalogues of orbital binaries. One of them is a 6-orbital catalog, and the other is a catalog prepared in Santiago de Compostela by Dr. José de Cobo and his collaborators. Again, as I said, it's the best catalogs containing orbital binaries. However, they contain some drawbacks from our point of view, from point of view of these goals. So when we speak about orbital catalog, 6-orbital catalog, then we found no spectral classification and no parallax data in the catalog. Sometimes period or /and semi-major axis values were absent, and we have found about 50 misprints, and we have reported to the authors of the 6-orbital catalog. The other catalog also has uncomfortable format and it's pure availability. We have on the web not the recent version of the catalog. There is no orbital parameters uncertainty. Pair names are often written incorrectly. The photometry is rather old, and we also have some found some misprints or errors in the catalog. General drawbacks from our point of view of these two existing lists: they are not exhaustive, and they often contain several orbits per pair. It's extremely useful for study of a particular orbital binary, but it is inconvenient for us if we when we do statistics of orbital binaries and we would like to count a particular pair once and only once. So our step one was compilation of a list of orbits. To do this, we have joined these two catalogs. We keep systems without known distance, but we remove on this stage systems with unknown period and semi-major axis. Then we have got recent photometry and spectral classification from WDS, and we have taken some data from SIMBAT. These data are the following. Its coordinates, which will be useful for us in next stages to estimate interstellar extinction, magnitudes and spectral types if were absent in original catalogs and WDS. We have taken new refined parallaxes from SIMBAT database, and again we have taken some notes or remarks about spectroscopic and eclipsing features in the systems. That means that it's sometimes not double but a system of higher multiplicity. The format of the resulting list is the following. We keep almost all identifications, numbers in two catalogs, WDS, name, Hipparcos, and ADS number. Then we also keep number of pair in a system and number of for a given pair. Magnitude, spectral type, parallax with uncertainty, all of them with uncertainty. We estimate interstellar extinction based on galactic latitude of a system. Then we keep orbital elements from original catalogues. We keep grade in both catalog, grade of a particular orbit taken from these catalogues. We also have taken notes and indication on spectroscopic and eclipsing binarity. Some statistics of the resulting list. This list contains some 3,000 orbits for 2,000, 2,500 of pairs, and 1,500 of pairs have only one orbit, and other pairs have more than one orbit. Among these 2,200 pairs, 2,000 binaries, and some numbers, some amount of systems of high multiplicity. For 6,500 of orbits, there is no modern or even no photometry at all for secondary components. For 65 orbits, we have no data on spectral type of components, and for some orbits, parallax is unknown, 0 or negative. Our step 2 was to construct a refined list of pairs. I will remind you that the previous list contained orbits, and now we would like to keep one orbit per pair, trying to choose the best one. First, we have removed triple systems and systems of high multiplicity to try to make our statistics as correct as possible. It should be statistics of binary systems. Then we have removed pairs with unknown parallax, and we have removed orbits with pure quality. Quality is indicated in original catalogs. Then we have selected one, presumably best, orbit for every pair based on orbit's quality, but as a rule, different orbits for the same pair have the same quality. But here we can compare dynamical and photometric mass of systems. And now how we can calculate different masses. I mean, how we can calculate masses with different ways. First, it's obviously the third Kepler law. If we have semi-major axis and parallax and period, then we have the sum of masses in this orbital binary. But we also can use the photometry, and again with known parallax and estimated interstellar extinction dependent on coordinates and parallax, we can have luminosity of a components. Using some mass-luminosity relation, we can estimate mass of a given component and then mass of a system. The third way to estimate mass of a star is the spectral type. We have some mass spectrum relations, different relations for different luminosity classes, which we can use to estimate mass immediately from spectral classification. So for orbital binaries, it's really a Klondike for mass estimation. For orbital binaries, we can estimate mass with these three ways, and comparing these three results, we can find, for example, which parameter is wrong. For example, parallax is included in these two forms, but is not included here. Then we can make some conclusions about how we can rely upon this mass. Is it correct or not? If possible, we also estimated uncertainties of these masses. This is a list of mass luminosity relations which we use to calculate photometric masses, and to calculate uncertainty of dynamical masses, we made some estimation for Santiago catalog because, as I said above, there is no estimation of orbital parameters, no errors of orbital parameters in the catalog. As a result, our list of pairs contains some 600 orbits. It means 600 pairs, a 600 system, as we keep. Okay, thank you. As we keep one orbit per pair and one pair for system. Two dynamical masses less than 0.1, which is strong and obviously incorrect. Some dynamical masses have mass larger than 100 solar mass, which is again incorrect and indication that something is wrong for this orbital binary. And on this view graph, I display you the results of comparison of dynamical mass with photometric mass, and here dynamical mass with spectral mass. The scale is different on these two view graphs, and the number of points are different as well. For example, here we have less points because we know spectral type for not for all binaries, and only for those binaries we can calculate spectral mass. So looking at this diagram, we can choose points with strange behavior and study them more carefully. Possible for discrepancy between dynamical, photometric, and spectral mass. This is a list of reasons. I think that it's exhaustive list, but probably we missed something. Probably we have a wrong parallax. In this case, we will have wrong dynamical and wrong photometric mass. Probably orbital elements are incorrect. It influences to dynamical mass. Wrong spectral type. If we have an error in temperature class, then spectral mass will be incorrect. If we have an error in luminosity class, then this true mass will be incorrect, etc. Third body, unresolved binarity, variability. For some types of variability, the spectrum will vary, and for all type of variability, we will have some errors in photometric mass. Then we try to correct our sample for selection effects. Magnitude difference between components, brightness of the first component, and distance, semi-major axis of a binary. We consider, we think that our set is incomplete out of this area. And also here, we consider our set is incomplete out of this area. And here, you can see the description of these rectangles. And as a result, we have selected 200 systems. And for these 200 systems, we can give some statistics. Gray, all 6,500 systems, and black selected 200 systems. And here you have distributions for masses, for it is a total mass of a system, for eccentricity, semi-major axis, and period. Playing with this, we can make some conclusions about history of star formation, about initial mass functions, so about formation of wide binaries. Of course, the resulting distributions are still distorted by some selection effects. For example, selection effects connected with the inclination of the orbit. The probability to discover an orbital binary, of course, depends on the inclination. We didn't count on this. We didn't count it here. So they cannot be directly, they cannot be mistaken for initial or present day distribution of binary parameters. So they cannot be directly used. However, they can be used to construct the initial mass function and star formation history of wide binaries. And this is a subject for our future study. Observations to determine spectral types and magnitudes and distances. It's really a vital problem. This result was recently published in Astronomy and Astrophysics. And concluding my talk, I would like to thank the organizers for the invitation and the audience for your attention.